Okay, so now let's do some exercises for some of the random variables that we already have introduced. Let's see if we can calculate. Let's talk about how we can calculate their expected values. Okay, so first example is going to be the dice example that we've talked about. And in particular, the situation in which we have let's start with a single six-sided die. So let's let U be the number of spots on a fair six-sided die. And what we know is that the mass function is equal to 1/6 over all possible values. And by the definition of the expectation, it's a sum over the values 1 up through 6, 1/6 times I. So it's 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. We can do the math. 7/2 or 3.5. First thing to point out, which I haven't pointed out yet, is that 3.5 is not one of the possible outcomes. That's fine. It doesn't have to be. So even though we're saying in some sense, we expect the outcome to be 3.5, even though it's impossible for the outcome to be 3.5. That's not a requirement for expectation. Okay. Now, in general, we can talk about having a U is discrete uniform. And what that means, discrete uniform on a set N, what that means is that the distribution of U is 1 over N for all values in the set, 1 up through N. And the expected value of U in this case, sum from I equals 1 to N, 1 over N times I, is 1 over N times the sum of the first N positive integers, which we have a closed form for. So the sum of the first N positive integers can be calculated as N times N plus 1 over 2. Of course, the N's cancel, and what we're left with is N plus 1 over 2. In the case of 6 above, we saw it was 7 divided by 2, 6 plus 1 divided by 2. Now, okay, so that's the uniform distribution for one die. If we were to take 2 dice, and we define S as their sum, well, I'm not going to actually do the calculation, but turns out we can argue that the expected value of S is 7 by symmetry. What do I mean by that? Well, in the triangular distribution, we have symmetry. 2 and 12 have the same mass. 3 and 11, 4 and 10, 5 and 9, 6 and 8, and then 7 has the highest mass. So everything on either side of 7, equidistant from 7, has the same mass, and so things are balanced out. They have to be balanced out at 7 in some intuitive sense. But we can also note that the expectation of S can be thought of as the expectation of U1 plus U2, which is equal to expectation of U1 plus expectation of U2. Seven halves plus 7 halves, this is equal to 7. So more on this later, because we haven't actually justified why we're allowed to do that. We will at a later time. But that's an important shortcut that we're gonna want to make sure we're aware of as we move forward, because it comes up all the time. Let's talk next about the binomial distribution. So now let's suppose we have binomial random variable, binomial n and p. Then how do we calculate? Then we know that Pn of k is n choose k, p to the k, q to the n minus k. So the expectation of n is the sum k equals 0 to n of k times n choose k, p to the k, q to the n minus k. Okay. Now what we can see here is if k is 0, then the term is going to be 0. Okay, so we can take that term out and just go k equals 1 to n of n choose k, p to the k, q to the n minus k. But now we're summing from k equals 1 to n. So actually what I want to do is I'm going to take an n out and a p out. It's a little bit of a trick, and you kind of have to just get used to doing this, which is that I want to manipulate this sum in such a way so that the thing inside the sum adds up to 1. Okay. And so what I'm left with here is k equals 1 to n of n minus 1 choose k minus 1, p to the p to the k minus 1 no. K equals 1 to n minus 1 choose k minus 1. I'll leave the p in there for now. P to the k, q to the n minus k. Then I'm going to do a change of variables. So I want the index to go from k equals 0 to n minus 1. And now, so I have n minus 1 choose k. I have to pull the p out, and I get p to the k, q to the n minus 1 minus k. But this here is the probability mass function of the binomial with n minus 1 trials and success probability p, and it's the sum over all possible values from 0 to n minus 1. So it's the sum of all probabilities, all possibilities of that random variable. So the sum has to be equal to 1, and we're just left with n times p for the binomial. So those are a couple of examples. This is an important trick of being able to manipulate probabilities so that we pull out certain parts and what we leave inside looks like the mass function, and we have to be able to recognize that it's a mass function of a random variable. And when we do that, we know that since we're summing over all possible values, we know that the sum has to be 1, and it drops out, and what we're left with is the expected value or the probability or whatever it is that we're trying to figure out. So that's a common technique that we use in this course. Here we saw it in the case of calculating the expectation of a binomial random variable. We're going to see this in a number of other cases as we move on.